Welcome to Brain Vision.
The force diagram for this problem looks something like this. We have gravity pulling us down with magnitude mg, and we have the force is equal to kV that they're referring to in the problem. That's slowing the motion down through the fluid. There is an acceleration in the vertical direction, so when we apply Newton's second law in the y direction, we get mg, because I'm defining my positive direction to be downward, minus kV is equal to mass times acceleration of the object. Now in this case, our initial velocity is equal to 3 mg over k, and since the terminal velocity in a fluid is equal to mg over k, our initial velocity is equal to 3 times the terminal velocity. Now the textbook does pretty much the exact derivation that this problem is asking for, except they just give us a different initial velocity in this problem. And so I'm going to borrow one of the equations that the books use. And so I'm going to start at the point here where you have a separated equation is what it's called. And we just need to remember that our initial velocity is 3 times the terminal velocity. And so this means that the lower bound on our separated equation is the initial velocity, which is that. And then the final velocity we just indicate by v. But the integrand is the same that the book uses. It's v minus vt. And now when we integrate this, we get ln, absolute value, of v minus vt. We're evaluating this at v and at 3 vt. When I evaluate at v, I plug v in for v. So I get that. And I'm subtracting it evaluated at 3 vt. Well, 3 vt minus vt is 2 vt, so I just get this. Now I'm going to use a property of logarithms, which says that the difference of two logarithms is those two arguments divided by each other. So this is v minus vt over 2 vt. And then I'm just going to shift the minus signs around. I'm going to add a minus sign in the denominator, and I'm going to add a minus sign in the numerator by swapping the values there. So I'm going to leave it there for the moment. And so let's move on to the next page. And we get that the previous expression is equal to ln of v over 2 vt minus 1/2. I just split up the fraction. And then I'm going to borrow another thing from the book. This is just equal to minus k over mt, which is really the other half of the separated equation. Now I'm trying to solve this for v, ultimately. And so we need to exponentiate both sides so that we can remove the logarithm. And so exponentiating both sides gives us a new equation. It gives us v over 2 vt minus 1/2 is equal to e to the minus k over mt. The exponentiation killed the logarithm, and then I just get this term over here. Now I'm going to add a half over, and I'm going to multiply both sides by 2 vt. When I do that, I get the final answer, which is 2 vt 1/2 plus e to the minus k over mt. And that's the final answer. If you're confused at all about the process I used, the book does pretty much the exact same thing, leading up from equation 5.5 to equation 5.10. The only difference between their derivation and ours is our initial velocity was 3 vt, so we had to plug in a different lower bound here. But that's it. And that's the final answer to the problem. It is right here.